have a few more basic ingredients about extra dimensions in general, and then I want to move on to warped extra dimensions right away, because I think that's the most important and exciting topic, at least when we are trying to apply it to these composite Higgs models. So what we said about extra dimensions is that if I take a 5D scalar field, yes, from the 4D point of view, it will appear as a tower of massive scalars. Yes, and that tower is called the KK tower. Whether or not there is a zero mode, that depends on if you're adding a mass term in the 5D or not. If you don't add one, then at the n equals 0, you will get a massless mode. Okay, so now the next story that you would like to do is do the same for gauge fields. Yes, so now you start out for a KK decomposition with a gauge field, and here there will be a little bit of a complication. Namely, the complication is, of course, what you naively expect is that there is an A mu and an A5. Yes? So from the four-dimensional point of view, yes, this will appear like a gauge field, like a 4D gauge field. And this fifth component, the extra dimensional component of the 4D gauge field, will appear like a scalar. Yes? I mentioned that at the very beginning of this series, yes, that this scalar could be important, yes, because this could play the role of the Higgs. And indeed, eventually in the final model that hopefully we will get to at the end of this lecture, that will be the story, that this A5, yes, will actually provide, the degree of freedom that will look like the Higgs. Now there's a little bit of a complication here, yes, which is related to the counting of the number of degrees of freedom, yes, because as you know, in 4 dimensions, yes, a massive and a massless gauge field have a different number of degrees of freedom. Yes, a massless gauge field, yes, so the n equals, let's say, m equals 0, massless gauge field has 2 degrees of freedom, yes, but the higher n's, yes, by n I mean, the Kaluza-Klein number that is telling you, at what level you are in this Kaluza-Klein tower, yes, that has 3 degrees of freedom. Okay. So again, the naive expectation is that you do the same story as for the scalar. You get a massive Kaluza-Klein tower for the gauge field and a massive Kaluza-Klein tower for the fifth component, yes, and that's not quite right, yes, because a massive gauge field already has 3 degrees of freedom, yes. And of course, the other question is, so how many degrees of freedom are there in a 5-dimensional gauge field? Yes, let's assume that this is a massless 5D gauge field. Yes, so that would be the analog of a massless 4-dimensional gauge field, which has 2 degrees of freedom. So in 5 dimensions, this one would have 3 degrees of freedom. Yes. So, yes, so that would be sort of like the analog of the 2 transverse components in 4 dimensions. Yes, in 5 dimensions there would be 3 transverse components. Yes, so a massless 5D gauge field has 3 physical degrees of freedom. Yes. And so what happens is, yes, that you see that at the massless level, that 3 can indeed break up to a massless 4-dimensional gauge field and a massless 4-dimensional scalar. But at the higher n level, there will only be a massive 4-dimensional gauge field. Yes? So what happens is that at the higher level, the gauge field is going to eat the tower of massive gauge bosons are going to eat the entire tower of, what would be the massive scalar tower for the A5s. Yes. So actually, the right KK decomposition, the physical content of the KK decomposition of a gauge field will be, there's a tower of massive gauge fields, and there's a single massless mode for A5. Okay, and actually, that A5 massless mode may or may not be there, so that depends on what kind of boundary conditions you are going to impose on the extra dimension. So we'll discuss that in great detail later on. Okay, so the physical content is, you have to be careful. There's nothing really, difficult here. And if you do it, I have it in the notes written out completely. I will not go through the details, but of course the way you can see this whole story about, you know, the gauge field eating the A5 is that when you are writing out the 5-dimensional Maxwell-Lagrangian FMN, yeah, so these will be now, you know, 5-dimensional indices. You will get terms of the form, yes, d mu A5 minus d5 a mu times d mu A5 minus d5 a mu. Yes, so you can see that there will be indeed terms, yes, that are, you know, d5 a mu, yes, times d mu A5. There will be these cross terms, yes, that are providing the mixing, the bilinear mixing between the gauge field and the scalar. So it is like the Goldstone boson, yes, like the story of an Eaton-Goldstone boson. So you can see that that mixing that is needed in order for the gauge field to truly, you know, be able to eat the fifth component, is actually already present in that Lagrangian. So you can choose a gauge where, you know, the A5 is really set to 0, and you know, you can really fulfill this whole story. Okay, so again, that the details are described in the notes, but this is the important physics there. Very good. Of course, if you have a higher dimensional gauge theory, yes, so if you have not 5 dimensions but 4 plus n dimensions, yes, just to make sure that we understand exactly what is happening here, yes, so if I have a 4 plus n dimensional gauge theory, yes, then what will happen is you have, again, a mu, and then you have here A5, A6, you know, and then A whatever 4 plus n. Yes, so you will have here n scalars. Yes, and then what will happen is, well, you know, you can guess what happens. Yes, you will have one entire tower of massive gauge fields. Massive gauge fields. And then you would naively think there are n towers of scalars, but what happens is that one combination of those scalars is going to be eaten. Yes, so you will have n minus 1 towers of scalars. Yes, plus there will be one additional mode that corresponds to sort of the 0 mode, you know, that would be paired up with the 0 mode of the gauge field. Yes, plus one single mode. Okay, so that would be the story here. Yes, very good. Now you could play the same game, for example, with the graviton. Yes. Yes, so for the case of the graviton, yes, so you're describing the graviton in terms of the metric. Yes, so in 5 dimensions, yes, you will have a GMN, a 5-dimensional metric, and then what is the physical matter content for that? Yes, let's do it immediately in n extra dimensions. Yes, so here you have the G mu nu, here you have a bunch of gauge fields, a mu, and then here you have a bunch of scalars living in the symmetric n by n lower part here. So this would be some scalars. And then, of course, the massless level, you just get exactly what you see here. You will get a 4D graviton. Yes, you will get n massless gauge fields. Yes, and then you will get these bunch of scalars. Yes, at the massless level, this n times n minus 1, n times n plus 1 over 2, yes, scalars that are coming from this symmetric part. But at the massive level, the first thing that has to happen is that the graviton at the massive level, yes, massive 4D graviton has 5 degrees of freedom, yes, and that is actually going to eat one gauge boson plus one scalar. Yes, so the graviton, there's a massive graviton in 4D. Yes, so that's like a massive spin 2 particle. Yes, so that now has the full, spin, 2, 1, 0, -1, -2, 5 degrees of freedom, while at the massless level, yes, it's just a helicity 2 particle, so it has only 2 degrees of freedom. So a massive graviton has 5 degrees of freedom. Yes, so it has to eat one of these gauge fields. Yes, eat one gauge KK tower plus one scalar tower. Yes. And then, of course, now I will have, you would think you have n massive towers for the gauge fields, yes, but one of those has been eaten by the graviton, so you will have n minus 1 massive gauge towers. Yes. And then you can count how many scalars are left over, yes, because every one of these is going to eat a bunch of scalars, yes. So n minus 1 was eaten here, and then 1 was eaten there, so you have to check out of these symmetrics how many scalars are left over, and you can do the counting, yes. So you started out with n times n plus 1 over 2, that's a symmetric, and then 1 was eaten by the graviton, and then 1 was eaten, n minus 1 were eaten by the gauge fields, yes. So in the end, you will have n times n minus 1 over 2 massive scalars. Okay, so again, this is just to give you an intuition that you have to be careful when you do the KK decomposition. Yes, I mean it's pretty trivial, but there are a few subtleties, and that is related to the fact about the number of degrees of freedom of a massive versus a massless field is changing. So there will be these little subtleties. Again, it's not very hard. Okay, so that's one important concept that I wanted to say before moving on to warped extra dimensions. And the other important concept is the matching of the couplings. The fact that, of course, in higher dimensions, if you take, for example, a gauge theory in higher dimensions, that will be a non-renormalizable theory. Yes, the gauge coupling will not be dimensionless. Yes, so we have to sort of try to understand how to do the matching of the couplings if you go from a 5-dimensional theory to a 4-dimensional theory, both for gauge couplings and for example, the gravitational coupling, the Planck scale. Okay, so matching of couplings. That's the second important conceptual issue. Yes. So again, the fields, the dimensions of the fields will be different in a higher dimension than in 4 dimension. Yes. So for example, if I take a scalar field, yes, its action in 4 plus n dimensions, yes, d5 phi squared, yes, there's a kinetic term, will still have the same form as in 4 dimensions, but of course now there's a 4 plus n dimensional integral here, yes, the action should still be dimensionless. Yeah, so this is still dimension 0 here. Yeah, so that will tell you that you have here 2, because you have 2 derivatives, plus 2 times the dimension of the field must be equal to 4 plus n. Yes, because now you have a 4 plus n dimensional integral. Yes, so what you get is that the dimensions of the dimension of a scalar field in 4 plus n dimension is 1 plus n over 2. So in particular, in 5 dimensions, scalar field will not be dimension 1, but it will be dimension 3/2. Yes, in 6 dimensions, it's going to be dimension 2, etc. Yes, very good. Now you can do, of course, the same thing for a fermion. Yes, so in a fermion, you have the Dirac Lagrangian or Dirac type Lagrangian. So there's a single derivative. So what you will find is that the dimension of a fermion in n dimensions is going to be to 3/2 plus n over 2. Yes? So we know in 4 dimensions it's 3/2. Yes? In 5 dimensions it's going to be dimension 2, for example. Okay, very good. Now, how will the couplings look like? Yes. Well, for example, how will a gauge coupling look like? Yes, so you will have a covariant derivative dm equals dm minus I g5, let's say in 5 dimensions, yes, times am. Yes. So now this derivative is still dimension 1, yes, but now the gauge field has the same dimensions as a scalar field, yes, is not going to be, for example, in 5 dimensions, not going to be dimension 1, but it's going to be dimension 3/2, yes. So that means that the gauge coupling, yes, has to have dimension -1/2, yes. So this is dimension 3/2 here, yes, so this should be dimension -1/2. Okay, and then the question is, so that's the 5-dimensional coupling, and how will a 4-dimensional observer see, what the effective 4-dimensional gauge coupling for the 0 mode will look like? So what is the effective 4D gauge coupling? Yes, well, what you are supposed to do is you are supposed to take your full 5-dimensional field, yes, expand it in the KK tower as I sort of outlined it for you. Take the 0 mode, yes, because the 0 mode for the gauge field is going to be, corresponding to a 4-dimensional gauge theory, yes. Plug the piece of the 0 mode here in, yes, and then perform the integral over the extra dimension. Okay, so what will happen here is, yes, that the 5-dimensional gauge field, yes, will look like, in terms of the 0 mode, there will be a flat 0 mode here, a mu 0 divided by root 2 pi r. Okay, and it's going to be usually, at least, actually even in the warped case, the 0 mode for the gauge field is going to be always flat, so there is, meaning, this will still be, of course, a function of x, but there will be no non-trivial profile along the extra dimension, yes, so that's, the 0 here means, yes, so that means it's the n equals 0 mode, yes, meaning that in our previous example yesterday when I wrote, the compactification on a circle, yes, the n told you, how many times you were wrapping around the extra dimension, yes, so there was a sign n times y over r, yes, so this is the n equals 0 mode, so there's no y dependence here, yes. So what you can see is, if I now think of this covariant derivative in terms of a 4-dimensional covariant derivative, yes, this will look like d mu minus I times g5 over root 2 pi r, yes, times a mu 0, plus other terms that I don't really care about, yes. And now this one will look like the covariant derivative, yes, from the 4-dimensional point of view with respect to the true 0 mode, the one field that will look like a 4-dimensional gauge field. Okay, so this combination is what I'm supposed to be identifying with as the effective 4-dimensional gauge coupling of that gauge theory corresponding to the 0 mode of the 5-dimensional gauge field. Okay, so what I get is that G4 equals G5 over root 2 pi r. Okay, in this simple case when I just compactified in a circle. Yes, actually you can go ahead and check, and it's not a very difficult exercise, that if you have flat many extra dimensions, the relation between the 4D and the 5D gauge coupling is just going to be given by the volume of the entire extra dimension. Yes. It's 3-level, yeah. Yeah. So this is the simplest thing, yes. So the general form of this matching is G4 squared. Come on. Cannot stand this. Equals G4 plus n squared divided by the volume of the extra dimensions. And again, this is assuming that the extra dimensions are flat, so this is usually only applicable in this simple form to toroidal compactifications. Okay, so that's very important, yes, so that there's a relation between the higher dimensional and the lower dimensional couplings. Okay, of course, the same story goes for gravity. Similar story about the matching for the gravitational interactions. Yes, the only difference is that, of course, the gravitational coupling already in 4 dimensions is dimension full. So what you are supposed to do is you're supposed to be matching the higher dimensional, more fundamental Planck scale to the effective 4-dimensional Planck scale. Yes, so what you're supposed to do for gravity is take a 4 plus n dimensional gravitational action. Yes, so the gravitational action is usually given in terms of this simple Einstein-Hilbert form. Yes, so you have a 4 plus n dimensional integral over the 4 plus n dimensional Ricci tensor. Yes, or curvature, the trace of the Ricci tensor, 4 plus n dimensional curvature scalar. Yes, and then of course whatever coefficient stands here, yes, that is what you will be identifying with the fundamental higher dimensional Planck scale. Okay, so here there will be a 4 plus n dimensional Planck scale, yes, and to make sure that you have the right dimensions showing up here, so you know that in 4 dimensions, yes, it would be m Planck squared. Now here you added n additional integrals, yes, so this will be now to the 2 plus n dimensions. Okay, so this is the generalization of the 4-dimensional gravitational action to higher dimensions. Yes, so in 4 dimensions, just to remind you, the action is m Planck squared times integral d4x root gr. Yes, so we take the same form, yes, except now, of course, it's an integral over the extra dimensions, so that will bring you n additional integrals. Yes, so that lowers the dimension by n. Yes, so you will add that back by raising the higher dimensional Planck scale not to the 2nd power but to the 2 plus n dimensions. Okay, and then of course you can start playing the same game here. Yes, you can say that, well, the graviton is supposed to have a 0 mode. Yes, I just erased that decomposition. Yes, so there is the 5D graviton, or higher dimensional graviton is supposed to contain a 0 mode. Yes, that will give you a piece here that is the R calculated just from the 0 mode, and then you will have here just the root g4 showing up. Yes, and then something has to make up the dimensions between the higher dimensional Planck scale and the 4-dimensional Planck scale. Yes, well, the rest will be an integral over the volume of the extra dimensions. Yes, so you will have to perform the n-dimensional integral, yes, over the volume of the extra dimensions, and that is what is going to give you the matching relation between the 4-dimensional and the higher dimensional Planck scale. Okay, so the matching for the gravitational interactions is m Planck squared, so that's the effective observed Planck scale is going to be the higher dimensional Planck scale times the volume of the extra dimensions. Okay, so that's at least in the case when the extra dimensions are flat. Okay, so this is a relation that is very strongly using the fact that this is a flat extra dimension, and it will be very different for warped extra dimensions. Okay, very good. So of course, these things have been known for many decades, since the 1920s, yes, and people have, not become super excited about extra dimensions for the reason that, well, they were imagining that, you have just a single theory. If you try to get a natural theory, that doesn't have, sort of hierarchies of scales included already for you. So a theory with a single scale. Yes. What would be the size of the extra dimension have to be? Well, you see the volume is showing up here in the matching between the gauge coupling, the higher dimensional gauge coupling, and the four-dimensional gauge coupling. Yes. So the higher dimensional gauge coupling is, of course, dimension full. Yes. So in a very natural theory, with a single scale, you would say that, well, the 4 plus n dimensional Planck scale is given by whatever this natural scale, this single scale of the theory is. Yes. This is a mass dimension. Okay. So this is the single mass scale of the theory. Yes. And the gauge coupling, of course, now is dimension full. So if you sort of, don't want to introduce many hierarchical scales into the theory, you would expect this to be also given by the appropriate power of the same scale here. Yes. So you can check, we have calculated what the dimension of that coupling is. Yes. So this would be m star to the minus n over 2 power. Yes. So this would be, a sort of natural theory where there's only one mass scale. Yes. But then, you go ahead and try to calculate, how large this m star would have to be. Yes. Well, this m star would have to be setting the volume of the extra dimension. Yes. Because we know that our observed four-dimensional gauge couplings are order 1 dimensionless numbers. Yes. So from the gauge coupling, yes, we know that this m star would have to set the volume of the extra dimension also, yes, because we know that once I match it to the four-dimensional theory, I have to recover the gauge coupling of the standard model. Those are order 1 dimensionless numbers. Yes, so that will tell me that the volume, yes, is set by, 1 over m star, to the appropriate power, whatever the dimension is. So m dimensions would be this. But then, now I'm going to go to the matching of the gravitational coupling, yes, and that's set by the same volume, and eventually I'm supposed to recover their m Planck, yes. So from the matching, from the gravitational matching, I will find that, m star should roughly be of the order of m Planck. Yes? So that would tell me that the size of the extra dimension in this theory where which is supposed to be natural, doesn't have a lot of scales introduced, should be of the order of m Planck, 1 over m Planck. Yes, so super duper tiny. Yes. So even if they are there, it's safe to neglect them certainly for our lifetimes. Okay. So that's why, these extra dimensional theories, where obviously people knew about it, it shows up in string theory, but the assumption was for many, many decades that if they exist, they are really, really tiny, yes, and they will not be important for phenomenology. Okay. So the big change that has come, that was at around the end of the 90s, was the realization that actually, this kind of scaling can be upset by the presence of additional objects called branes. Okay. So branes could change expected scaling of these couplings. Of the size of the dimensions. So branes are lower dimensional objects. Yes, so these are lower dimensional objects. And you can, in field theory, sometimes objects like this show up as solitons. of the theory. In string theory, they show up as more fundamental objects called d-branes. And in our story, we are not going to really try to ask the question what really produced those branes. Yeah, so we will just accept that they could be there, that such objects exist. They again, they could have dynamical origin, or they could be more fundamental as they are in string theory. And the most important thing for us is that they could sort of change the estimate about the size of the extra dimension. Yes, and in particular, the first proposal that people got really excited about, that's the one that I will not talk about very much, is called the large extra dimension. Yeah, so in that case, the assumption was that actually our standard model is completely stuck to a so-called 3-brane. So a 3-brane would be a 3-dimensional spatial hypersurface that is floating somewhere in the extra dimension. Yes, so we have the so-called 3-brane. Yes, and the standard model is stuck here. Yes, so if you're producing your E plus E minus experiments, that's stuck on the brane, but of course gravity can escape in the extra dimensions. Okay, so the nice thing about this theory was that in that case you still have to keep the matching of the 4-dimensional gravitational coupling to the higher dimensional gravitational coupling. Yes, but this relation here, yes, there is no meaning to this anymore. Yes, because in this theory, the gauge theory is sort of fundamentally 4-dimensional to begin with. Yes, so there's nothing to match with. Yes, so there's only one matching relation that you have to obey. Yes, you don't have the second one that wants to force a relation between the volume of the extra dimension and the higher dimensional coupling. Yes, so in this case you only need to match the gravitational couplings yes, and then you can start messing around. Yes, because previously I was telling you that the constraint was that I didn't want to introduce a bunch of different fundamental parameters. I only wanted to introduce one fundamental 5-dimensional coupling, higher dimensional coupling. Yes, but now I don't have that. Yes, I have the standard model stuck on the brane, and the only thing that I will have is the 4-dimensional gravity theory matched to the higher dimensional one. Yes, so now what you can imagine is you can have volumes for the extra dimension to be much larger than this fundamental Planck size volume. Yes, and the bigger I make the volume here, yes, the lower the higher dimensional Planck scale is actually going to appear. Yes, so I can start increasing the volume of the extra dimension. Yes, and that will decrease this M4 plus N, the 4 plus N dimensional coupling, which I will just call M star. Okay, just so that I don't have to write M4 plus N all the time. Yes. So the extreme limit that the so-called large extra dimensional theorists were taking was take this all the way to the TeV. Yes. And they said, well, it would be really exciting if we lived in a universe, yes, where the fundamental scale of gravity was actually equal or roughly equal to the scale of the weak interactions. Yes, because then I could sort of declare that, well, actually that's the only fundamental scale in my theory. Yes, and M Planck is actually not really a fundamental scale. It's sort of a mirage. It's just because I have these very large extra dimensions around, and what happens is that actually, this large extra dimension is going to dilute the strength of the gravitational interactions when I look at long distances. Yes, and gravity, when I look at long distances, will sort of naively appear as if it was a force much weaker than the weak interactions. Yes, But of course, if I went to very short distances, I would start seeing the fact that, you know, the fundamental strength of the gravitational interactions is actually the same as that of the weak interactions. Yeah, so that was the proposal of Nima et al. It's called large extra dimensions. So I'm not going to go through the details because I want to get to warped extra dimensions as quickly as possible. You can, you can try to do this matching. You can calculate, so how large the size of this extra dimension would have to be. It would depend on actually the number of the extra dimensions that you have. Turns out for n equals 1, that's way too large, is bigger than the solar system, so that's excluded. But already n equals 2 was roughly allowed, was about a millimeter size extra dimension. And if you increased n, then it was smaller, but smaller than millimeter, but still pretty large compared to, for example, 1 over TeV. Okay, so that was a very nice idea. It has sparked a lot of interest in this extra-dimensional theories. There are nice phenomenological consequences. Again, they are in the notes, or you can ask Javi in the afternoon about it. The one thing I would like to say about this is that, so this was originally sold as possibly a solution to the hierarchy problem. Yes. And again, the solution would be that, well, there's only one fundamental scale, is the TeV scale, and that's basically the fundamental cutoff of everything. Yes. Of course, there's one, really bothering issue here is that, you say that there's one fundamental scale, yes, but you say it at the same moment when you say, but the extra dimensions are really, really large, yes. And they are set by, some completely different scale, namely the one that is going to give me the right matching, so truly you don't have just a single scale. Yes? So in that case, the question about the hierarchy will be translated to the question of, okay, if I only have one scale, m star, and that's a TeV, yes, then why is the radius of the size of the extra dimension not also 1 over TeV? Yes? So why is the extra dimension then so large compared to that one natural scale? Yes? And that's a really difficult question. Yes? So it's basically, I would say it's not really a solution to the hierarchy problem. It's a reformulation of the hierarchy problem to, why is now the extra dimension so large compared to the one natural scale that your theory is supposed to have. And again, so that's a difficult problem. It's not like, there are no possible ways to do it, but they are, again, it goes a lot of technical details in order to really try to stabilize it at this exponentially large scale. Okay, so that's the story of large extra dimensions. All right, so now I would like to move on to the other type of extra dimension that people have been talking about mainly over the past 2 decades, which is the story of warped extra dimensions. And the Dsc Fd correspondence, and then hopefully I will be able to show, how to use this warped extra dimension at the end to build a complete model for the minimal composite Higgs. Okay, so first of all, I would say that unlike the large extra dimensional theory, this is a true solution to the hierarchy problem. Except, as we will see, the true solution is just not a different solution to the hierarchy problem. It's sort of the same as the composite Higgs type of idea. Yes. So large extra dimension would is truly different. Yes. I mean here the conceptual way of getting around the hierarchy is really different than in any other approach. The question is just, is it truly solving it? Yes, because you have to stabilize the size of the extra dimension at an exponentially large value. Here, this will be really a true solution to the hierarchy problem. It's just not going to be, a fundamentally different one, as we will see from the Dsc Fd correspondence. It is sort of related to the type of solutions that we have been discussing before. Okay, so it is a true solution, but it's related by the Dsc Fd correspondence is related to the pseudo-Goldstone boson composite Higgs models. Okay, so the main aim for the remaining hour is to sort of, explain, how that relation is coming about, and to really give you finally the model that, most people are taking most seriously, which is an extra-dimensional version of the minimal composite Higgs model, where the Coleman-Weinberg potential is truly calculable. It's actually finite. It tells you what the spin 1 and the top partners are, etc. Okay, very good. So let's get started with the warped extra dimension. So in that case, we have a single extra dimension. So that's already different from the large extra dimensions. Yes, in the case of large extra dimensions, actually the single extra dimension was the only one that was excluded. Yes, because that would have been so large that it's bigger than the solar system. Yes, so here is a single extra dimension. Yes. But the main difference is that it will have one additional ingredient compared to what we had before, that this extra dimension is not going to be flat. There will be a non-trivial metric along the extra dimension. Okay, so there is a non-trivial metric okay, so and that it had a particular form. It is called an 5-dimensional anti-de Sitter metric. Okay, ds squared equals r over z squared times just dx squared minus dz squared. So there are different parametrizations of how to write this particular metric. The original paper by Randall and Sandrum were not using this particular parametrization. They were using an exponential. Yes, of course, it's just a matter of coordinate transformations. I think, this form of the metric is, the physics is more clear. So I usually use the one where there is an overall factor in front of the entire 5-dimensional, all the 5-dimensional distances. Yes, of course, the one where that was written in the Randall-Sandrum paper. Yes, so there was a warp factor in front of the 4-dimensional coordinates and no warp factor in front of the 5th coordinate. So that's just a coordinate transformation between these two coordinates. Usually the one which is, so this one is called the conformally flat metric, meaning that there is an overall warp factor. Yes, and up to that overall factor, it's a flat metric. So this is called the conformally flat form. Meaning that up to a prefactor, yes, it's a flat metric, yes, and this term here is called the warp factor. And of course, as I said, there's another form of it, which is the non-conformally flat one. So usually people are pretty consistent of calling these coordinates the z coordinates. And the ones that Randall and Sandrum were using, they call those usually the y coordinates. So whether people use z or y already gives you a hint of which metric you're using. I think, as I said, the physics of this metric is much more transparent than the other one, so I prefer to use this form of the metric. Okay, very good. So you have this warp factor, so this non-trivial metric. And what you have in addition is two branes that are sort of cutting off the space-time at some finite values of this coordinate z. Yes, so there will be a z equals r. There will be a brane, which is called the UV brane. And at z equals r prime, which is an exponentially large value. Okay, so this is an exponentially large there will be a so-called IR brane. Okay, so the metric is sort of decaying as r over z squared. Yes, in between the UV and the IR brane, and so this is sort of the warp factor. Yes, and this scale R here, yes, so that is what is setting the overall mass scales in this theory, yes, so the R is called the ADS curvature, yes, in comparison to R, to the sort of more fundamental mass scale, the mass scale that is showing up in the metric, yes. This one is the same, yes. So this is the same. Of course, you know, that's kind of a matter of choice, but the important thing is that it's something of the order of R, yes. And then the other brane, it's at an exponentially large value. Okay. Very good. So, and again, you know, this R is called the ADS curvature, and there will be one brane sort of, you know, ending your space-time at a scale that is comparable to the ADS curvature. Usually we literally take it to be Z equals R, yes, and then the other one is at some exponentially large values. Okay, so the most important story that you have to remember about these warped extra dimensions is that because of this non-trivial warp factor, the mass scales are changing as you are moving along in the extra dimension. Okay, so the mass scales, the characteristic mass scales that are characterizing the strengths of the interactions as you move along the extra dimension is actually not constant. Yes, so this point here and that point there, yes, are not equivalent in the sense that the intrinsic mass scales are actually going to be changing. Yes, so I'm going to write it like this. The M of Z, the characteristic mass scale, as you move into, so this is usually called the bulk of the extra dimension, the interior, as you're moving away from one brane into the bulk, yes, inside the bulk, the characteristic mass scale is going to be given by R over Z times M of R. Yes, so whatever the characteristic scale was over here, yes, as you are moving into the extra dimension, yes, that characteristic mass scale is going to decrease. Yes.
Can you understand where is the real work here?
I have not told you yet. Okay, so that's, of course, you know, that's what we are trying to build up. But okay, so let's try to take the simplest example where I'm going to tell you, you know, just define. So that was the original paper of Randall and Sundrum, where we will just define a particular model to illustrate, you know, this this mass dependence, this spatial dependence of the mass scales. So the RS1 model, Randall-Sundrum 1 model. And so that's an illustration of this idea. Yes. So in that case, what you have is you are going to put the Higgs boson on the IR brane. Okay, so the Higgs boson is a four-dimensional object. It's living on this second end of the world brane. Yes. So assume that the Higgs is stuck to the IR brane. Okay. And, you know, for simplicity for now, let's assume that the entire standard model is stuck to the IR brane. But, you know, what matters just is that it's the, you know, is the story about the Higgs. So you have these two branes, and the standard model, or the Higgs, is stuck here. Yes, and of course gravity is not stuck there. Gravity, you cannot, you know, you cannot tell where it's stuck. You cannot proclaim it. You have to check, you know, well, gravity is the fluctuation of the metric, so the gravity is going to be wherever it wants to be in this particular background. Yes, you have to, you know, you have to solve the Einstein equations and see what the fluctuations of the graviton look like, and that will tell you where the graviton is. Yeah, so that's not something that you can just proclaim. Okay. Very good. So in that case, let's see how the Lagrangian for the Higgs field would look like. Yes. Well, so I'm just going to write here, you know, an action for the Higgs that is stuck on the IR brane. And of course, the important thing that I want to write here is to make sure that I have to use here whatever the induced metric, the induced four-dimensional part of the metric is from this five-dimensional metric. So the induced four-dimensional part is you have to do the right projection of the 5D metric in this case, because you have, you're projecting it onto a flat brane. Yes, you basically just take, whatever the prefactor of the four-dimensional components are, except you are not taking it at z equals r, yes, but you are taking it at z equals r prime, where this prefactor is very, very small. Yes, so you go ahead and write your four-dimensional action for your Higgs, yes, but you use the induced metric. Yes, so you use the metric that is, coming from the five-dimensional metric, but is projected onto the position where your IR brane actually is. Yes, so this is called the induced metric. Yes, and then you just write down, whatever your kinetic terms for the Higgs would be, d mu h times g mu nu, again induced. Yes, and then you write here a potential for the Higgs, h absolute value squared minus v squared. Yes, so that would be the, the usual Higgs action. Yes, you can write covariant derivatives, doesn't matter for the argument for now. Yes, the important thing that matters is to keep track of this induced metric factors. Yes, so what is the root g induced? Yes, well, you have to take this r over r prime. Yes, and you have to take the square root of that, and then you have to take the, so this is a determinant here. Yes, this is the this root g means it's a determinant of that metric. So you will get 4 powers of r over r prime. Yes, times, now of course the ordinary four-dimensional d4x, and now of course this metric factor was taken into account, so I don't have to write any more root g's. Yes, d4x, I assume the rest is just flat. Okay, and then here you get another d mu h squared. Yes, times you get another power of r prime over r squared. Yes, minus lambda times h squared minus v squared. For the Higgs, yes, how would the Lagrangian for the Higgs that is induced, that is localized at the position where this weird metric is non-trivial, yes, its prefactor is not 1, yes, how would that look like? Yes, it's pretty trivial. Yes, it will just pick up these specific prefactors. Yes, those are just some numbers. Yes, and then what you see is, yes, well, I mean, it looks like an ordinary Higgs Lagrangian, yes, except the kinetic term here is not properly normalized. Yes, so you will have to rescale the Higgs field. Yes, so you will have to rescale the Higgs field h tilde equals r over r prime times h. Yes, in order to get back the proper normalization for the kinetic term. Yes, and once you do that, yes, what will be the effect? Yes, well, I get rid of this r over r prime factors. Yes, because that's how I have rescaled my field, by definition. Yes, it also gets rid of the rescaling here because there was an h to the 4 term here. Yes, so that had then already the right factor. Yes, so in the h to the 4, the prefactors completely disappear, and the only place where there will be a non-trivial effect is that this v is going to be rescaled. Yes, so once I do all of this, the effect in terms of these properly normalized Higgs field is going to be a simple Lagrangian. Yes, integral d4x. Now canonic kinetic term for the Higgs. Yes, everything is fine in terms of quartic, and then the only thing that is non-trivial here is that I will get this explicit the V, the thing that is setting the Higgs wave, is going to be explicitly rescaled. Okay, so the physical Higgs wave is going to be not V, but V times R over R prime. Okay, that's the only effect that it has. And so that's exactly the thing that I was telling you here, yes? I had a Lagrangian, yes? It had no mass parameters, yes, because there's a kinetic term and the quartic term. The only mass parameter that was introduced here explicitly was this V factor, yes? So this is an explicit mass term, yes? And because this mass is not introduced at z equals r, but at z equals r prime, actually is going to be rescaled according to this rule here. Yeah? So the physical mass parameter, yes, is going to be rescaled. So if r over r prime is exponentially small,
But again, we still have this large scale of order r prime over r.
right,
And also, we artificially put Higgs stuck on the second brain.
right. So those are clearly issues, yes. And it turns out that this story is very different than the large extra dimensions because in this case, stabilizing the metric at an exponentially small r over r prime is actually very, very simple. Okay, and that's the one thing that is easier to see in the other set of coordinates, in those y coordinates, because it turns out in the y coordinates, because in that set of coordinates, the metric looks like e to the minus k times, actually it looks like e to the minus y over r, yes, in the other set of coordinates, yes. So actually that y distance there is not exponentially large, but the exponential comes from the fact that the prefactor itself has an exponential function. And it turns out, so that's something that I will not go through, but it's very, very easy. There's a very simple stabilization mechanism that just tells you that, yes, y at, like 10 over r, stabilizing at 10 over r or 30 over r is super easy. Okay, so stabilization is easy here. But it's of course true that without telling you where the stabilization, if that's possible or not, at this point it looks like, I'm just shoving this in by hand, yes. But when you see the Dsc Fd correspondence also, you will understand that this should be something possible because it will have a simple interpretation in terms of the dynamics of gauge theories. And but anyway, just from the 5-dimensional picture, yes, purely it turns out that the stabilization is easy and it goes under the name of the Goldberger-Weiss mechanism. But yes, so that's an additional ingredient that, again, I will have no time to discuss, but in many of my previous lecture notes, and it's included there. Yes, and the story about the Higgs being stuck here, well, so that's an important question, and we will discuss that in detail later on. It turns out that the Higgs, of course, doesn't have to be exactly stuck here. It can only, what will be needed is that it could be a bulk field that is peaked on this brane. And as we will try to do the KK decomposition in this background, we will see that that's something completely natural. Basically, all KK decompositions are such that things are either peaked on one brane or on the other brane. Okay, so actually, I agree that this looks artificial, but again, this is just a toy example for now to give you an idea of what the essence of the mechanism for the higher dimensional solution of the hierarchy problem actually is. But of course, as you build more and more realistic models, it becomes more and more complicated, but the essence will be still the same. So the essence will be that there's a Higgs. Actually, the Higgs will be an A5, and you will see the A5 is naturally going to be peaked on this brane. Okay. All right, very good. So again, the upshot is that, this natural scale for the wave of the Higgs is exponentially small, or, well, it's whatever, wherever I put this brane, yes, that's what the natural mass scale is. So I could have started out with a theory where, for example, you know, every scale is set by roughly this r, yes, and this r could be, let's say, 1 over m Planck size, yes. For example, v is roughly of the order of 1 over r also, yes, and yet end up in a theory where the natural mass scale of my Higgs wave is actually much lower, yes, it's going to be set by 1 over r prime. Okay, so the idea is that r is of the order of 1 over m Planck, yes, r prime would be something of the order of 1 over TV. So sometimes this is usually called, sometimes it's also called the Planck Brain, and this one is usually also called the TV Brain. Yes. And start out with a setup where I take a theory where every mass parameter is set by r, yes, set by 1 over m Planck. So I put here a Higgs wave that is of the order of 1 over m Planck, yet just the fact that I'm putting it away from the UV brain, yes, is going to warp it down. It will warp down all the physical mass scales and still give you an exponentially small Higgs wave. Okay, so that would be the source of the hierarchy problem. Now, one question that you should ask is, does it really solve the hierarchy in the sense of what happens to the gravitational interactions? Yes, because if I also warp down at the same time the scale of gravitational interactions, then I'm in trouble. Yes, because I mean I want to explain the difference between the scale of the electroweak interactions and the gravitational interactions. So you can go ahead and, well, I don't know, I may need this figure, but you can go ahead and try to calculate what now the matching of the 5D to the 4D Planck scales are. Yes. So the matching of the gravitational interactions. And so you go ahead and do the same thing. This is m star cubed times integral dz integral d4x root g5 r5. Okay, so that's another really nice exercise to do in the afternoon if you want. That's I'm not going to go through the details. What you're going to find here is that actually the matching of the gravitational scales is totally different here than the matching in the case of the flat extra dimensions. Okay, so the matching of the 4D and the 5D Planck scales in this theory is going to be m star cubed times r times 1 minus r squared. Okay, so you would say, well, no, doesn't it look like the matching for the, there's m star cubed times r, but r is not the size of the extra dimension, yes? The size of the extra dimension is set by r prime, and it barely depends on the size of the extra dimension, yes? In fact, sort of the shocking thing when people first saw this, many people couldn't believe this, yes? What you could do is you could take r prime all the way to infinity, yes, so take the size of the extra dimension infinitely large, and yet the 4D Planck scale is going to remain constant. It's going to approach a constant. It's not going to go to 0. Yes, so you can even take, so it barely depends on the size of the extra dimension. So in that sense, it's truly completely different from the matching of the gravitational scales in the flat extra dimensional case. Yes, so there, it's m Planck squared, yes, was given by m star, for a 5 dimensions, yes, would be this times whatever the radius is, yes, and if I take the radius to infinity, yes, then the 4-dimensional Planck scale would go to infinity, meaning that the interaction strength goes to 0. Yes. Of course, it just means that, well, in that limit, it's not a 4-dimensional gravitational theory. It's a stupid idea to try to try to match a theory with an infinite extra dimension to a 4-dimensional gravitational theory. While here you are saying, oh, even in the limit when the size of the extra dimension goes to infinity, something essentially 4-dimensional about the gravitational interactions is still there. Okay, so that's something really interesting and nice. And again, you know, there is a second version of the Randall-Sundrum theory, yes, which is called RS2. Yeah, so that was not trying to explain the hierarchy problem, was just saying, look, here is an interesting example of how to get a 4-dimensional gravitational theory out of a theory with an infinite extra dimension. Yeah? So that was called the RS2 model. RS2 is when R prime goes to infinity. Of course, in that case, you know, you wouldn't imagine that the standard model lives on the IR brane because there is no IR brane. Yeah, so in that case, they assume that the standard model just lives on the UV brane. So there's just one brane here. So this is Z equals R. This is where the standard model is. It has its hierarchy problem because I didn't introduce this other mass scale. But the interesting part about this theory was that it's a theory with an extra dimension, an infinite extra dimension, yet gravity behaves 4-dimensional. Okay, so the question is, you know, how is that possible? Yes, well, actually, it's not that super hard to understand. What you're supposed to do here is to explain, you know, what the physics underlying, this weird behavior of gravity is, to just, you know, find the profile of the graviton zero mode. Yes. And again, you know, it's not super hard, but you have to go ahead and expand, you know, the 5-dimensional Einstein equation. You do have to do perturbation around this non-flat metric and find out, you know, just what is the profile of the graviton zero mode. And what you find is that it's actually exponentially peaked around the UV brane. So it's peaked around the UV brane. Okay, and that explains everything. Yes. So the picture is that you have your UV brane, you have your IR brane, yes, and the graviton is exponentially peaked around the UV brane, yes, and the Higgs, again, you know, is either stuck here or, as we'll see later, is exponentially peaked around the IR brane. Yes. Now, it explains why I can remove the IR brane and still get a normal gravitational theory. Yes, because, well, okay, so this is, the graviton already goes to zero anyways exponentially as you go away from the UV brane. Yes. So it doesn't matter for it, you know, whether you add this tiny additional contribution from the tail or not. It remains a normalizable mode. Yes. So the graviton zero mode remains normalizable as R prime goes to infinity. Yes. So we understand why, you know, there's no contradiction, and this RS2 is a reasonable theory, and it's truly, you know, approximating 4-dimensional gravity. There are corrections there. That's why it's a very interesting kind of theory. And it also explains, you know, at least in this 5-dimensional sense, you know, the origin of the hierarchy, yes? Which is saying that, well, I told you that the mass scales are decreasing as I move along the extra dimension, yes? And gravity feels mainly the part where the mass scales are very large, yes? So that's why the Planck scale is going to be super large, yes? But the Higgs feels mainly the region of the extra dimension, yes, where the mass scales are very small, yes? So the characteristic scales of the weak interactions are going to be exponentially suppressed compared to the characteristic mass scales of gravity, yes? So m star times r over r prime would be roughly the TV scale, yes? And that is exponentially smaller than m Planck, which is of the order of m star. Okay, so that's the story of how this RS type model, at least, you know, from this 5-dimensional point of view, is solving the hierarchy problem. Okay? But of course, the thing that I would like to get to as quickly as possible is, you know, make the connection to the kind of theories that we were discussing before. So I would like to get to the Dsc Fd correspondence in a moment. Right. And it will have also KK modes. Yes, of course. And then the question is, you know, what happens to the KK modes? Where are they localized? Yes. So I get to that in a moment. Okay. Of course, the graviton KK modes, for example, in this RS2 theory, yes, they will give you corrections from a ordinary 4-dimensional gravitational theory. Yes. But it turns out those corrections are under control and they are small. Okay, so this will still, if your standard model lives here, yes, the zero mode will be the main effect. For example, if you're calculating the Newton's potential between two objects on the UV brane, and there will be some small corrections from the KK modes. And it turns out that, you know, they can be made small enough that the theory truly looks like a 4-dimensional gravitational theory, even though you have this very large, you know, or infinitely large extra dimension. Okay, so before I get to Dsc Fd, I would like to exactly address this question of what happens to the KK modes. Yeah, so first, I will not do it for the graviton, just because the equations are, you know, more complicated. As usual, I will do it for a scalar field. Yes, so how do we do a KK decomposition for a scalar in the warped extra dimension? Well, again, you know, we have to do exact. So now I'm going to add the scalar into the bulk. Yes. So I'm going to move away, start moving away from the story where the Higgs is, you know, just stuck on the UV on the IR brane. Yes. And I'm going to add a scalar into the bulk of the extra dimension. Yes. So the action would look like integral r to r prime dz d for x root g. Now this is a 5-dimensional root g. Yes. And then you have here dm phi star dn phi gmn minus, for example, a mass term. It's just the simplest story. Yes. So you go ahead, you take the equations of motion. There will be a bunch of, you know, g factors showing up. Yes. So the equation of motion is, let me just write this out once. It's root g times gmn dn phi minus root g m squared phi equals 0. So that will be the equation of motion. Yes, the 5D equation of motion for a bulk scalar. And then what you are supposed to do is, of course, you are supposed to do a KK decomposition as previously discussed. Yes, so you are expanding these modes. You don't know what these basis expansion functions are. Yes, I mean in the case of the flat extra dimension, we knew that it's just going to be sine and cosine. We use the Fourier series. Here there will be some expansion functions. Yes, and these will be what are called the profiles of the KK modes. Yes, so these are called the wave functions of the KK modes. And what exactly the structure of the profiles of these KK modes is going to mainly determine, you know, what the physics of these KK modes is. Yes. And then, of course, there will be ordinary 4-dimensional fields here. So these are the 4D modes. These are their profiles, their wave functions. Yes. And then usually we put in some normalization factor, 1 over root r, sum over n, just to get the dimension. So this way, this is going to be a dimensionless profile. Yes. And then this is now an ordinary dimension 1 4-dimensional field.
These profiles are like agent functions of in some space.
I'm sorry? They are, well, so I don't know yet what they are. Yes, so I have to determine them, you know, by plugging in. So the assumption is that these should be ordinary 4-dimensional modes. Yes, so I know what their 4-dimensional equation of motion of these guys should be. Yes, they should just be box phi equals some m squared. I don't know what the m squared is, but it's for the equation of motion should be just box phi equals m phi. yes, or m squared phi, yes, and that will then, give me the equations, for this profile. So that's the technology that you are supposed to be using here, yes. So you do that exactly, yes, what I was saying, and you get a simple, just a single differential equation for these profiles. And what you're going to get here is, I mean, the details don't matter that much, but I think, the concept of how to do it is sort of, part of this, whole higher dimensional 3 over z times dz plus mn squared minus r over z squared m squared fn of z. Yeah, so it's exactly what we just said, yes. I shove this ansatz into my 5D equation of motion. I assume that the 4-dimensional one satisfies the equation box, 4-dimensional box acting on phi equals mn squared times phi, yes, and then I will just get a single equation for the profiles, yes. So this is a ordinary Schrödinger type of problem with a slightly weird normalization, and the solutions will just be Bessel functions, okay. Solutions, and that's something pretty generic for these warped extra-dimensional theories. Solutions are Bessel functions. In fact, they are going to be powers times Bessel functions, z squared times j alpha mn z plus, so there's some constant here, plus c2 times z squared y alpha mn z. And the alpha is, so that's an important thing, 4 plus m squared r squared. Okay.
So we have some cylindrical symmetry of rotation around the axis?
I guess you can.
Because we have Bessel functions.
I don't know. I don't know if how to interpret it in terms of symmetry. Probably. Anyway, the important thing is the Bessel functions are very generic. That's what is going to be always showing up in these. And the important thing is that all of these Bessel functions are such that they are usually some exponentials times, so they are usually powers times sine or cosine. Yes. So the Bessel functions for large values of z is powers times sine or cosine. So these are sort of the analogs. Yeah, so you can call them the warped sines and cosines. Yes, so these are the analogs of the sine and cosine that is appropriate for the for the KK expansion in the warp space. Okay. The most important thing about this is that all of these, yes, because it's powers, another power here, yes, they will always be peaked towards the IR brane. So all peaked towards IR. Okay. The only exception could be the zero mode. And whenever you have a zero mode, yes, then actually, you're not going to get Bessel functions, but you're going to just get straight powers. Okay, and you can show that the zero modes will have some simple powers. So just powers of the form f0z is z to the 2 plus or minus that famous factor 4 plus m squared r squared. Okay. So all the KK modes are localized towards the IR. Yes, so that means that actually the KK expansion, yes, its natural mass scale always is going to be, it's going to be a tower of TeV scale particles. Yes, it's you take a theory, put it in this extra dimension. The KK expansion naturally will give you a tower of KK step modes. Yes, so the KK tower, yes, will be sort of something like n over r prime. Yes. Now the zero mode, you don't know exactly, you know, which one, you know, so that could be on the UV, could be on the IR, yes. That could, you know, so that could be, so that depends on, you know, which of these modes you are getting, yes. What? This is for the scalar, The graviton is different, yes. This is, for the graviton is always on the UV brane. Okay. This is for a scalar, so that's slightly different for the graviton. So the graviton zero mode is always on the UV brane and it's decaying. So in the Z coordinates would be a power decay away from the UV brane. Yes, because exponential in sort of physical coordinates is power in the Z coordinates. Yes, because the Z itself becomes exponentially large. Okay. So again, so there's a KK tower, and the important thing is that the steps, yes, in the KK tower, yes, are going to be given by the TeV scale. Yes. Because all of these modes are exponentially localized on the IR brane. Yes. So you can see that, you know, for example, for, you know, if I put some, so you can see that in this theory, somehow, truly, with the two branes, yes, this TeV scale is what is actually going to be the emerging natural scale for most of the physics, except the graviton. Okay, so now let's get to the Dsc-Fd interpretation. Okay, so let's talk about Dsc-Fd. Sorry? It's a KK tower, yes. So whatever exactly the scale is, and you know, it's not exactly n over r because, you know, it's Bessel functions. So at the bottom, you know, you have to look at zeros for Bessel functions, but roughly, yes. Right. So there's a whole tower, yes. Always there's a whole tower. Unless you are, you know, just sticking stuff in on the brane itself, yes? Then, of course, there is no tower. Okay. Very good. Dsc Fd correspondence. So originally, of course, this came from string theory. And, of course, this was the big discovery of Maldacena, I guess almost exactly 20 years ago, yes. And what he found was, you know, if you take string theory on a particular background that was, you know, related to what we are talking about, ADS 5 cross S5, that was actually exactly equivalent to n equals 4 supersymmetric Susy gauge theories, the kind of theories that Lance likes. Okay. What is important for us is that this n equals 4 supersymmetric gauge theory is always a conformal theory. Okay, so that's why it's Dsc-Fd, yes, because the background was the essential part of the string theory background was the fact that you had this non-trivial ADS factor, yes, and the essential physics of the corresponding, you know, four-dimensional gauge theory was the fact that this was actually a conformal field theory. Okay. Of course, you know, you needed all the machinery of supersymmetry and, you know, string theory in order to really show that this is a, you know, that this is a true statement. Yes, now, what we would like to do is we would like to take some of the essential ingredients that inspired Maldacena and would try to generalize it to the kind of theories that we are talking about, which are not 10-dimensional theories. They are, just 5 dimensions, and they are not supersymmetric. Of course, there will be nothing even close to the kind of, proofs that are going through in string theory, but you can make it plausible that something like the Dsc Fd correspondence that is holding for the for the full string theory should be at play also in these simple-minded 5-dimensional constructions. Okay, so let's try to understand, where this essential ingredient about conformal symmetry and scaling is coming from. Yes, I basically already told you this story, but you can repeat it in a slightly different language. Yes, so you take your metric, your 5D ADS metric, R over Z squared times dx squared minus dz squared. Yes, and what you are going to do is let's move along the extra dimension. Yes, let's move along the extra dimension. So let me do a scaling where z goes to e to the alpha times z. Okay, so that's just saying that I have a particular point in the extra dimension, and now I'm going to move along somewhere further into the bulk. Yes, what happens then? Yes, well, what happens is that, okay, so this prefactor is going to change here. Yes, and the way I can compensate that is by also rescaling the 4-dimensional coordinates. Okay, so I can compensate that scaling the 4-dimensional coordinate by the same factor. Yes. Okay. So that's really it. Yes. That is explaining, roughly all the physics that we have been talking about until now. Yes. And it's explaining the heart of the Dsc Fd correspondence. Yes. What it's saying is that a motion along the extra dimension is equivalent to rescaling your coordinates in the 4-dimensional theory. Yes. So the further I go into the bulk, yes, I'm going to increase the length scale of my 4-dimensional theory. Yes. So that explains, for example, the story that I was telling you, that the mass scales are changing, the characteristic mass scales are changing along the extra dimension. Yes, sure, yes, because as I go into the extra dimension, that's like saying that I'm going to be probing a different length scale in the 4-dimensional theory. Yes. So moving along the extra dimension is basically, equivalent to, just just going along the, is doing a renormalization group running in the 4-dimensional theory. Yes. So this is a 4D scale transformation. And again, this explains my initial, premise about this theory is that, well, okay, so the mass scale is just, is just position dependent. Yes, that's exactly what this RS solution is taking advantage of. Yes, that the mass scale way in the bulk is much smaller than the mass scale over here. Yes, but of course, if I so that's the first and most important, entry into our Adsc Fd dictionary, which is that the motion along the z direction is equivalent to a renormalization group scaling in the 4-dimensional theory. Okay, so motion along z is equivalent to a 4D scale transformation. Yes. So this is also called the holographic renormalization group running. Yes. Well, because you're doing something in a higher dimension, yes, and that's going to be projected out into the four-dimensional theory, yes. This whole thing, the fact that you have a higher dimensional theory that has a corresponding four-dimensional picture, yes, that's usually called holography in this sense, yes. I'm sorry, the Landau poles, sorry. Well, again, this is supposed to be a conformal theory, yes. So there will be no Landau poles here, yes. So the idea is then that if I didn't have any brains in any UV brains or IR brains, yes, then this theory could be completely scale invariant, could be completely conformal, yes. So if I have no UV or IR brains, yes, there would be a conformal field theory corresponding to it, yes. So I'm going to be going through all the possible values of the z coordinate, yes, from 0 to infinity, yes. So I go through all of the ADS space, yes. That's like going through the entire renormalization group scale in a four-dimensional theory, yes. So if I have no UV or IR brains, yes, this Dsc Fd correspondence is going to tell you that this five-dimensional theory is actually equivalent to a true conformal four-dimensional field theory. Yes. What exactly that field theory is? Well, in the non-supersymmetric case, we cannot tell. Yes. Of course, Maldacena in some particular examples told you explicitly, what that is. It's of course a more complicated construction with 10 dimensions, string theory, supersymmetry, blah blah. We don't have that, but again, the assumption is that there is still going to be a corresponding four-dimensional conformal field theory. Okay. Again, of course, we have no proof for that, but that's going to be the starting assumption that something like that is still going to work here. Yes. The thing that I would like to emphasize is what are the additional things that we are doing when we add the UV brain, the IR brain, gauge fields here and there. How will those give you additional entries in this Dsc Fd correspondence? Yes. So first of all, how about the UV brain? Yes, well, if I add the UV brain, yes, that is telling me that, I try to go to higher and higher scales, but at some point, my space just ends. I cannot go to arbitrary high scales. Yes, so that has a very simple implementation. It's just saying that I have a cutoff for my CFT. Yes, I cannot go to arbitrary high scales. There will be a cutoff for the CFT, yes, at lambda is about 1 over r. Okay, so it's a conformal field theory, but now it's not a true conformal field theory. It's a conformal field theory with a cutoff. Okay, now the other ingredient is the IR brain. So that's more complicated. That's more subtle. Yes, because what we have seen is that if I have an IR brain at a finite distance, what I'm going to get is I'm going to get a KK tower, yes, with spacing given by roughly 1 over r, 1 over IR prime masses. Yes, so I have this KK tower. If I have the UV and the IR brains, yes, and this is at z equals r prime, then I'm going to get a KK tower where the spacing of these modes, yes, is going to be given by wherever I put this IR brain. Okay.
There is no difference what to switch on first. We can switch on IR brain, and there is also will be only.
Sure. Yes. Right. That doesn't matter, but the important thing is that they will have different interpretations. Okay. So the IR brain, again, the presence of the IR brain gives you this tower of KK modes, yes, that are spaced by the position of the IR brane. Yes. So what is that reminiscent of? Yes. Well, that's more reminiscent of taking a confining gauge theory. Yes. This is like a confining gauge theory, like QCD. Yes. With, you know, a tower of excitations. Yes. A tower of hadrons. Yes. So the interpretation of the IR brane is actually going to be very different from the UV brane. The interpretation will be that actually what happens here is that the CFT was spontaneously broken Right, but again, it doesn't matter whether, you know, they have their interpretations independent of each other. Okay, so this interpretation will still be correct even without the presence of the UV brane.
If we switch off UV brane, then
yes,
we will not get KK tower.
we will still get the KK tower because they are exponentially localized towards the IR brane. So what happens in the UV doesn't matter. Yes, it's like the graviton zero mode. Yes. It's a weird thing. It's like I told you for the graviton that I can remove the IR brane. Yes.
There is no expansion in series, but we will have
Well, again, you know, because it's, you know, because there's a mode that is exponentially localized here. Yes. What happens here doesn't matter. Again, that's the weird part. Yes. And then you can, well, there's one possible mode that becomes non-local, non-normalizable, which is the zero mode. Yes, so you have to worry about that mode. But this entire tower, all of these modes are localized on the IR. So that's really important. Yes, the entire tower is localized on the IR. So I can remove the UV. Still, the interpretation is that the CFT was spontaneously broken. Yes, and again, you know, the way you should think about it is that, well, a CFT is a theory with a zero beta function. Yes. For example, QCD is an example like that at very high energies. Yes. The beta function is very small because QCD is asymptotically free. Yes. And then what happens is it's sort of pretty close to conformal, and at some point, of course, you know, the couplings will become strong. You know, the beta function, you will start noticing that the beta function is non-zero. Yes. And you will generate confinement, chiral symmetry breaking, and this entire tower of modes. Yes. So this sort of interpretation is saying that it's as if, you know, this theory was, you know, really exactly conformal, and then suddenly the beta function became super large. Yes. So this is really an exaggerated limit of that. Yes. You know, if you really truly wanted to get that idea, you would probably not have an exact ADS metric, you know, around the IR brane, but you would, you know, start deviating from exact conformality. Yes. So this story here, the one where it's exactly ADS and then there is just a wall there, is sort of the limit where you have zero beta function, and then suddenly it becomes infinitely large. Yes. Of course, it's a toy limit. Yes, you can make it more realistic by turning it on more slowly, but you know, so people are talking about soft walls, etc. So I'm not gonna get to that, but that's the picture. Okay, the CFT was spontaneously broken, yes, and then created a mass scale, yes, like the QCD scale, yes, and you know, whatever fields there were, they will all have KK towers that are corresponding to the hadronic excitations of that CFT that became confining and strongly interacting. So there's one very clear way that, you know, this whole picture can be validated, which I will not talk about in detail, but there's an additional mode in the 5-dimensional metric which is called the radion. Okay, so the radion will roughly be setting the size of the extra dimension. Yes, and it turns out that that radion mode in the RS picture where you have both the UV and the IR brane is actually going to be an exactly massless mode, okay, without stabilization. And that can actually be identified, its properties completely, with the Goldstone boson corresponding to the spontaneous breaking of scale invariance, which is the dilaton. Okay, so there's a story here, which is that the radion is equal to the dilaton. Okay, so that's the way to truly, you know, make this picture that there's a spontaneous breaking of scale invariance emerging here, you know, very firm. The fact that there is, you know, whenever you think that there's a spontaneous breaking of a symmetry, you should think there should be a Goldstone boson, yes? Scale invariance is a global symmetry that is spontaneously broken. Where is its Goldstone boson? Well, the theory has it. It's the radion, and you can identify its properties, and it gives you exactly the right kind of coupling. Okay, so once you have this dictionary, a really beautiful picture is going to emerge for you. Yes, the picture will be that now there are two kinds of fields. Yes, you have your UV brane and you have your IR brane. Yes, and the modes that are localized close to the UV brane, yes, those you would call, from the point of view of the CFT, you would call elementary modes. Yeah, so the modes localized here, UV localized, they are called the elementary fields. Yes, because from the point of view of the CFT, yes, the composites of the CFT, they will all be localized around the IR brane. So whatever you put here is basically a mode that is external to your CFT. Yes? And then the IR localized ones are the composite modes. Okay, so those are, you know, the ones that are the composite excitations of the underlying CFT. Okay, now that's not all. Yes, actually there's one more really important part of the dictionary that yes. Right. So then, you know, like you know, from this picture, it's clear that, you know, the story that I was telling you that the entire standard model is on the IR brane is probably too naive. Yes, because that would tell you that the entire W is a composite. Yes. Well, we know that, for example, the photon, you know, doesn't look like, you know, a composite object very much. Yes. So that picture needs to be refined. Yes. So I would like to do that if I can take, you know, a few more minutes. I'm looking at Brando too. No. Okay. Very good. So there's one more really important ingredient here for the ADS-CFT that I really would like to get through, which is the story about the global symmetries and the gauge symmetries. Okay. So in ADS-CFT, there is also a very definite way of dealing with global symmetries. Maldacena told us that in his story, the way to deal with a global symmetry for his CFT, which was n equals 4 super Young-Mills, is to take a gauge field and put it into the bulk. Okay, so for Maldacena, let me write the continuation of the correspondence. So for Maldacena, the global symmetry was a gauge field in the bulk. And that was pretty clear in his case because, you know, he was explaining, you know, how to turn on, couplings for the CFT, which was living on the boundary of the ADS. And, you know, if you wanted to sort of, you know, couple something to a globally conserved current, then you needed to introduce a gauge field in the bulk. Okay, so the basic story, again, that we are taking from string theorists is that if the CFT has a global symmetry, you have to include a gauge field in the bulk. Okay, but for the case of Maldacena, when he didn't have a UV or an IR brane, yes, this was clear that it was completely a global symmetry always, because that gauge field did not have a normalizable zero mode. Okay, but in our case, when we have a UV and an IR brane, we can actually mess around and sort of, sometimes have a gauge, sometimes weakly gauge that global symmetry that he has, and sometimes not. Sometimes just keep it as a global symmetry, yes? So the zero mode of the gauge field turns out to be completely flat. Okay, so this is the zero mode of the gauge field. So that's flat even in the warped extra-dimensional case. Okay. And the other thing that is really important is that the corresponding A5 mode, yes, is going to have boundary conditions that are opposite to the boundary conditions of the corresponding gauge mode. So its boundary condition is opposite to A mu. Okay, so the story with the gauge and global symmetries is the following, yes? Well, you will have a gauge symmetry if, of course, this zero mode, this flat mode is remaining normalizable. Yes, so if A mu 0 has a flat boundary condition on both branes, yes, you will have a weakly gauge global symmetry, because you will have the zero mode, which Maldacena couldn't possibly have, yes, because he didn't have the UV and the IR brane, and this A mu 0 was always non-normalizable. Yes, if meaning, well, by weakly gauged I mean that there is a CFT which has its intrinsic gauge coupling, yes, which you are assuming is a strongly coupled theory, yes, and here on top of that, so compared to the interaction strengths of the CFT, yes, this one could be small, yes, that it's not related to the interaction strengths of the CFT. Okay, this is something that you can dial, you can make it small, yes, and usually you want to make it small because this is where the standard model is going to be, okay? The standard model gauge interactions, okay? So if A mu 0 has a Dirichlet boundary condition on the UV brane, meaning I set it to 0 on the UV brane, yes, that means I have removed this A mu 0 from the system, yes. If A mu 0 has Dirichlet boundary condition on the UV brane, yes, then I remove the zero mode, the gauge zero mode, so this will be just a global symmetry. Okay. Now, is this global symmetry broken or unbroken? Yes. Well, it depends on what happens on the IR brane. On IR brane, if I take the global symmetry and impose a Dirichlet boundary condition again, yes, then it's a broken global symmetry. If it's Dirichlet, it's a broken global symmetry. Okay. If it's Neumann, yes, then it's just an unbroken global symmetry of the entire theory. And now here comes the really cool part, yes. If it's Dirichlet, broken global symmetry. Neumann, unbroken global symmetry. Yes. Now here comes the really cool part. Of course, if it's a broken global symmetry, there's gotta be a Goldstone boson. Yes. If this whole picture makes sense. So where is the Goldstone boson? Yes. Well, what I was telling you is, if I made the A mu Dirichlet both on the UV and the IR brane, and in that one case, this A5, which has opposite boundary conditions always to A mu, is going to be flat on the UV, flat on the IR. In that case, A5 is going to have a zero mode. Yes. And that A5 zero mode is going to produce the Goldstone boson for you that you are interested in. Okay, so in this case, A5 will have a zero mode. Okay, so just to not make Brando completely unhappy, I will only take 15 more minutes. No. No, but I will take a few more minutes just to explain now how in this picture I would get the minimal composite Higgs. Yes, because I did promise that to everybody, so that would be a shame to leave without that. Okay, so the minimal composite Higgs from warp extra dimensions. Yes, well, so what we are supposed to say is that, okay, I have a UV brane, I have an IR brane. Yes, I have to put the SO5, the global symmetry, I have to put into the bulk. Yes, now I'm supposed to make sure that, you know, it's only the SU2 subgroup, yes, that is gauged for it. Yes, so on the UV brane, I'm going to break SO5 to SU2 cross U1. Yeah, so that will tell me that at low energies, I only have an SU2 cross U1 global symmetry. Gauge symmetry, yes, because that's the only gauge interactions that I can see at very low energies. Yes, and on the IR brane, I'm going to break SO5 to SO4. Okay. This whole structure, together with the Dsc Fd, will imply that I will have the Goldstone boson. The Goldstone boson is going to be an A5 component of the gauge field, yes. So you can go ahead, that's described in the notes, you can identify it, yes. And the other beautiful thing is that this theory will already have, you know, the spin 1 partners built in. The spin 1 partners, yes, are the KK modes. To, you know, the ones that are cancelling the quadratic divergence for the standard model, for the W and the Z. Yes, so when we were talking about, you know, composite Higgs models, we said I need spin 1 partners and I need top partners. Yes, those are the objects that cancel the quadratic divergences. Okay, they are already there, yes, by construction, and it's actually very easy to see that in this example, you know, the Coleman-Weinberg potential is going to be completely finite. Okay, so I didn't have time to talk about introducing fermions, so I don't know, maybe if Javi has time in the afternoon, you know, introducing fermions into this theory, that would be really, really a useful thing. There's a really beautiful story there also. You know, there you could have elementary and composite very nicely separated, and you can make the top mainly composite, the light standard model fermions mainly elementary by having them peaked on one brane or the other brane. And again, the top partners will be automatically there, yes, because they will be the KK modes of the fermions that you are introducing there. And again, the story is that the Coleman-Weinberg potential, just by construction, is going to be completely finite. Okay, so actually not even log divergent. All right, I think I have to stop now, and thank you for your attention.